Good evening, everyone. Hello. So, today we are here for our sixth tutorial session of the course Petroleum Technology. Let me share my screen. Okay. I hope my screen is visible to you all. Okay. So, just a second. Okay. So, let us start with today's tutorial session uh, on the topic extraction of valuable cuts from the upgradation of uh, upgradation of various cuts that we get from the various residual cuts that we get from the crude oil distillation. Okay. So coming on to the first procedure, which is the gasoline processes. So basically, as I told, the gasoline, it is one of the most important side cut that we get from the atmospheric distillation unit, or it is the simplest cut that we get from the crude oil distillation. So gasoline producing processes start with oil. It is mainly started when we feed crude oil into the atmospheric distillation unit. As I told, in the atmospheric distillation unit, crude oil is fed, where crude oil is split into naphtha fraction that boils up to 180 degrees C. It is basically this gasoline is extracted mainly from the naphtha fractions, and naphtha fraction, it is the first liquid cut that we get from the crude oil distillation. The first liquid cut that we get from the atmospheric distillation unit. Okay. So about 40, so basically we firstly from the, suppose this is the atmospheric distillation column. From the above we get of gases, gas C1, C2 fraction. Then after that we get naphtha. Okay. So naphtha, it is basically C3 to C7 fraction of up to 180 degrees C boiling point. Okay. The C3 to C7 fractions up to 180 degrees C, and this naphtha is further sent to the debutanizer and splitter, where the butane portion is separated from the naphtha to give out to separate out the C4 fraction, that is the butane part is separated from the naphtha, and it is further splitted into two portions: light naphtha and heavy naphtha. So this light naphtha, its boiling point is up to 80 degrees C, and heavy naphtha, it is from 80 to, sorry, this light naphtha, it has a boiling point up to 90 degrees C, and this heavy naphtha, it has a boiling point from 90 to 180 degrees C. Okay. So this light naphtha, it makes almost, sorry, So this light naphtha portion, it makes almost, so this light naphtha, it it is basically the 40% portion, and this heavy naphtha, it is basically the rest 60% balanced portion of the naphtha. Means the total naphtha consists of almost 40% light naphtha and 60% heavy naphtha. So why I am telling you this, that this 40% portion, this light naphtha portion, this whole 40% of the naphtha produced during crude oil distillation, it is basically it acts as a feedstock for petroleum, for petrochemical applications. Okay, it basically this 40% of all the naphtha produced from crude oil by simple distillation is required to satisfy the demands for petrochemical feedstock. Okay, and the remaining balance of this naphtha, that is the remaining 60% heavy naphtha, it is converted to gasoline, and the gasoline and the but this 60% heavy naphtha, which is used for the which is converted to gasoline, it is not enough to meet the demands, to meet the market demands of gasoline. So this gasoline portion, this remaining gasoline portion, what will happen? Then the remaining gasoline shortfall is satisfied from various conversion processes of heavier residual products. Okay. Various other procedures are also responsible for fulfilling the gasoline needs, such as during, from the coker unit or from the FCC unit or from the hydrocracker unit. Also, we get some amount of naphtha, which is further used. The naphtha from all the secondary processes, secondary processing units is also taken in, which is combined the mean combining this whole naphtha, remaining 60% from the crude oil distillation, and from the and other smaller amount of naphtha from different secondary processing units of residual products. Also, so we get some naphtha. Combined naphtha is further used for the conversion to conversion to gasoline. Okay. The C4 fraction or butanes from the naphtha are obtained as lighter head of the naphtha, which has octane number. This butane, as I told you, this naphtha is sent to the debutanizer, where butane is removed from the naphtha. Okay, but this butane has very good octane number of close to 100. But it also, this is the advantage. It is good. It has a good octane number, but it has also a negative, mean a disadvantage, which is its high reed vapor pressure, which will, if added to the gasoline, what will happen? Vapor pressure of gasoline will be very high. So we cannot take that risk. That's why this naphtha is removed in the debutanizer. Okay. Okay. But now what we see that in the debutanizer, butane is removed, but due to its advantage of this octane enhancer, as it acts as octane enhancer, 5% of this butane is used in the gasoline blending component to limit the vapor pressure. Mean only 5% is added so that the vapor pressure does not get affected much. And moreover, it also helps in the octane enhancing. Okay. And surplus butane, remaining butane that we get from the debutanizer, that is used in the that is used as an LPG component with propane. Okay. As we studied earlier in the LPG, which is a C3 and C4 cut. Okay. So this C4 cut comes from this butane. The isobutane component of the butane stream is a necessary. From the debutanizer, we get all the C4 cuts. So along with butane, we get some amount of isobutane also. So isobutane component of the butane stream, it is a necessary feedstock to the alkylation unit. We will further study what is this alkylation. Okay. We will study in the coming slides. C3C4 olefin stream that is derived mainly from FCC unit. C3C4 olefin stream, basically the C double bond C mean an unsaturated stream, that is the double bond compounds of the C3 and C4 cut which are they are mainly derived from the FCC unit, fluidized catalytic cracking unit. They are used for the preparation of MTB, which is a very good octane enhancer. Okay. So one stream that that exists in C5 C6 fraction is from the crude distillation unit we get from the naphtha, as I told, it is from C3 to C7 fractions. Okay. So from the naphtha, we get C4, debutanizer, remove C4. Then from naphtha, some amount of C3, C4 olefin streams are also there. The naphtha that we get from the FEC unit, that consists of some olefinic portion also. Then it consists of some C5, C6 fractions, which are isopentene, which is basic isopentane. It is an isoparaffin which has a hydrocarbon, which is a hydrocarbon of 93 reaction octane number, research octane number, and a valuable this acts as a valuable component for aviation gasoline. So if this isopentane is also there in the naphtha fraction, it can be used for aviation gasoline, for blending in the aviation gasoline. Then the virgin light straight naphtha is also sometimes directly added to the gasoline pool if its octane number is in the permissible range. Mean we are telling here is that the light straight run naphtha that we get from the atmospheric distillation unit, it consists of various fractions. Okay, so it needs to be converted to gasoline. So if there are some non-permissible components are present in the light straight run naphtha, then we need to remove it. But if it is of very good quality, this light straight run naphtha is of very good quality and has a very good octane number, then it can be sometimes directly added to the gasoline pool. What is this gasoline pool? It is basically gasoline consists of various components. So basically, it is a kind of pool in which different components of the gasoline is added along with some octane enhancers, then some anti-corrosive components, as it is used in a motor engine. So it should not consist of impurities that may corrode the engine. Then it may consist of some anti-gum agents, anti-foaming agents. All those are added in the gasoline pool. Okay. More often, it has to be isomerized first. So the light straight run naphtha, it is sometimes added directly to into the gasoline pool, and sometimes it is isomerized. Meaning gasoline, as we know, it should have a good octane number. So for good octane number, it should have mainly components should be aromatics and isoparaffins. But this light straight run naphtha, it may consist if there are large amount of N paraffins present which are not desirable in the gasoline for good octane number gasoline. So it is sometimes this light straight run naphtha is sometimes isomerized also to convert these N paraffins to isoparaffins so that it may not affect the octane number of the gasoline pool. Okay. A large portion of the straight run naphtha goes outside of the outside of the fuel refinery for petrochemical production. As I told, 40% naphtha it is sent to the used as a feedstock for petrochemical production. Okay. Coming on to reforming. This is another term, reforming of naphtha. As I told that the naphtha consists of various components. They may be good for the gasoline production, they may be bad as well. So what is the main requirement for a good gasoline is that it should have good octane number. So what happens if the quality of naphtha is not up to the mark? We need to enhance the octane number of that naphtha. Okay, so reforming it basically is a process in which we upgrade the low octane naphtha to high octane naphtha. High octane motor fuel, basically high octane gasoline. And this upgraded fuel obtained after reforming is termed as reformate. Okay, it is termed as reformate. This process involves the reconstruction of the hydrocarbon molecules of naphtha constituents without changing the boiling range. The boiling range is kept similar. Only what is done, either we isomerize it or alkylate it or different or polymerize the hydrocarbon molecule. Basically, we just change the configuration of the hydrocarbon molecule without affecting its boiling range. Okay, these hydrocarbons are paraffins, naphthenes, and aromatics in the range of C5 to C12 range. Okay, naphtha obtained from catalytic or thermal cracking operation contains some olefins also. As I told, the naphtha that we get from the crude distillation unit, that does not contain any olefin. As we know that crude oil doesn't have any olefin contents, but from the secondary unit sometimes we get some olefin contents also, mainly from the catalytic cracking, or from the thermal cracking units we sometimes get olefin also. The reformed naphtha or reformate is the reformed naphtha or reformate is rich in aromatics and isoparaffins. As I told that we convert it to high octane motor fuel. So for being a high octane number, the main components required are the aromatics and isoparaffins. Okay, so if N-paraffins are present in the naphtha, they needs to be converted to aromatics and isoparaffins for its quality to be good. Okay, hydrogen produced in this process is used in and during this reforming, hydrogen is also produced sometimes. So that hydrogen produced in this process is used in hydroprocessing of different cuts. Okay, in different other processes also, where in the other places in the refinery where hydrogen is used, you can use the hydrogen that is produced in the reforming unit. Okay. Reforming is accomplished by processing the naphtha feed. How this process is done? By processing the naphtha feed at elevated temperatures, basically from 450 to 520 degrees C. Reforming is taken out at high temperature and moderate pressure of 4 to 30 bar or in the presence of oxygen. Okay. Catalyst uses mainly platinum based, and the reforming process mainly platinum or alumina based catalysts are mainly used, and the are mainly used during this reforming process. The reforming process is mainly of two types: semi-regenerative type and continuous regenerative type. Okay. So the UOP, that is Universal Oil Product, which is a company which first commercialized the reforming process in the year 1949, and it called this process at platforming. Why platforming? Because it used this plat came from the word platinum, as it used a platinum based catalyst, and forming came from the reforming. Okay, so it called this process of platforming after the name of platinum catalyst, and they also developed the continuous catalyst generation system. Okay, they also generated this continuous regeneration system. Coming on to the reaction chemistry of reforming, there are four different principal reactions which are involved in the reforming, which is dehydrogenation of naphthenes. Hydrogen is removed from the naphthene structure to convert them to aromatics. Okay. Then isomerization of naphthenes and paraffins. Isomerization of naphthenes and paraffins takes place to form isoparaffins. Okay. Then dehydrocyclization of paraffins. Here two processes are involved. Hydrogen will be removed. Mean cracking of the paraffins takes place. Firstly, cracking takes place, and then cyclization, then conversion of these cracked products into naphthenes takes place. Okay, this is the two procedure: cracking and formation of naphthenes takes place. Then further cracking of paraffins. In the cracking of paraffins, what happens is it breaks down. Cracking of this paraffins takes place to smaller paraffins, and sometimes olefins are also produced. Moreover, sometimes not isoparaffins, smaller paraffins, and sometimes olefins are also produced. Okay. So aromatics pass through virtually unchanged, and during this reforming procedure, what is our main requirement? We need to produce aromatics and isoparaffins. Okay. So what happens is these aromatics, they pass virtually without any changing. If aromatics are present in the naphtha, then they pass through the reforming procedure virtually without any change. Okay. And naphthenes, they dehydrogenate easily to form aromatics. Okay. Naphthenes basically are, suppose this is the naphthene structure without any double bond. Okay. This is a cyclic structure. Naphthenes are basically cyclic hydrocarbons without any saturated, basically saturated cyclic hydrocarbons. So when we dehydrogenate them, if it releases hydrogen, then it gives aromatics. Okay, so it easily releases hydrogen, it easily dehydrogenate and forms aromatics. Okay, naphthas with high paraffinic content give less favorable yields in terms of aromatics. As we know that for octanes, for good quality, good octane number, requirement is aromatics and isoparaffins. And if there are large number of n-paraffins, then the octane quality will be bad. Coming on to the first reaction, that is dehydrogenation of naphthenes. So dehydrogen of naphthene to the corresponding aromatics is a fast procedure. It is a fast process and it is an endothermic reaction and is favored by high temperature and pressure. Okay, as we can see here, this is methyl cyclohexane, which is a naphthene, and it has a research octane number of 75. It is dehydrogenated to give toluene, and 3 moles of hydrogen per mole of toluene produced, and this toluene has a research octane number of 100 plus. Okay. Next reaction is isomerization of naphthalene. An example of isomerization of naphthalene is conversion of alkyl cyclopentane to cyclohexane. Okay, this is methyl cyclopentane. It is also a cyclic structure, but it is a thermodynamically strained structure. Okay, so it is isomerized to give a cyclohexane structure. Okay, so aromatization of cyclohexane is the next step, which so this cyclohexane, it can be easily further dehydrogenate to give aromatics. Isomerization of naphthalene involves ring opening and ring arrangement. Okay, so this isomerization of naphthalene, what happens? It involves the ring opening. For firstly, this 5-chain ring opened, and then it rearranged to form a 6-chain ring. Okay, isomerization of paraffins. So paraffin isomerization reaction occurs rapidly at typical operating temperatures. And isomerization of paraffins, it produces isoparaffins from n-paraffins, thereby it increases the octane number. Okay, so here we can see this is n-hexane, which is a normal paraffin. It has a research octane number of 25. This is isomerized to give a 2-methyl pentane. Okay, the carbon number is 6 here only. It is a C6 cut. This is also C6 hydrocarbon, but with a side branching. Okay, so it is a isoparaffin, and we can see here the octane number has improved to to almost 3 times, which is 74. Okay, just a second. Coming on to the fourth type of reaction, which is dehydrocyclation of paraffins. This reaction is a difficult reaction as it involves steps, two types of reactions. Okay, it involves both cyclization and dehydrogenation of paraffins. Okay, so what happens is, firstly, it is favored by low pressure and high temperature. It takes place in low pressure and high temperature. So this and normal paraffin and heptane, it is it is hydrogenated as well as cyclized. Okay, so firstly, both the procedure takes place together. It forms a cyclic structure by removing 1 mole of hydrogen. Okay, and it forms methyl cyclohexane, which has a higher octane number of 75, whereas this n-heptane has a research octane number of 0. Coming on to the cracking, next type of reaction, which is cracking of paraffins. Hydrocracking of paraffin is a reaction which occurs with the hydrogen liberated from other reactions of reforming. Okay, in this other types of reactions, uh, they liberate hydrogen, whereas here hydrogen is used from the which occurs with the hydrogen. Mean this reaction takes place in the presence of hydrogen, which is released in the before three types of reactions. There hydrogen is liberated, and here hydrogen is used. Okay, it is a high temperature and high pressure reaction. In this process, some unwanted lighter products are obtained, which boils below gasoline range, and hence total liquid yield is diminished. Okay, this cracking of paraffins is not basically paraffins are not desirable in a gasoline cut, so it is cracked down into smaller products. So as we can say here, this N-decane, which has a research octane number of -53, it is broken down into sometimes it may form some isoparaffins as well as some smaller N paraffins also, as here it formed the N-butane, which has a research octane number of 94, and 3-methyl pentane, which is a isoparaffin, which has a research octane number of 75, which is much better than the original research octane number of the reactant, which is -53. Okay, coming on to different types of reforming processes. So as I told, there are two types of reforming processes. The first one is semi-regenerative reforming, and the second one is the continuous catalytic regeneration. Uh, 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 Continuous catalytic regeneration. Just a second. So the uh, semi-regenerative process, this process is continuously carried out for a long period of time, and catalyst activity gets reduced with time due to coke deposition. The catalysts are regenerated in the period of 6 months to 1 year. So basically what happens is, in the semi-regenerative type, there is a single uh, there is no continuous regeneration of the catalyst takes place. The catalyst works for a long period of time. Mean the reforming procedure takes place in the same catalyst, over the same catalyst again and again for a long period of time, until the whole catalyst gets exhausted by the coke deposition. And after the whole catalyst becomes completely inactive, then this catalyst is taken out for regeneration, and almost it works for a period of 6 months to 1 year. Okay, as the activity of the catalyst decreases, the naphthalene conversion, and moreover, what is the disadvantage, that as continuous reforming takes place on the same catalyst and coke deposition keeps on occurring, then with the time the activity of the catalyst is decreased. More with that, the naphthalene conversion and yield of the hydrogen is also decreased. Okay, mean the reforming yield as well as the hydrogen produced decreases. Okay, whereas in the continuous catalytic regeneration process, the regeneration of the catalyst takes place continuously in a special regenerator. Okay, and the regenerated catalyst is charged to the operating reactor in every single time. Mean after a single operation, after a single reforming operation, each time the regeneration of the catalyst takes place in a different regenerating regenerator reactor, and the regenerated catalyst is fed back again to the operating reactor. Coming on to the details of semi-regenerative catalytic reforming. So it indicates the unit is periodically. So the semi-regenerative catalytic reforming, is simply tells that this unit is periodically shut down to regenerate the catalyst. As I told, that they run for a long time, and when completely the catalyst is exhausted, then the unit is completely shut down to regenerate the catalyst. So the naphtha feed hydrotreated to naphtha feed, which is fed into this SR reactor. Firstly, it is hydrotreated to remove if there is some amount of trace elements of sulfur and nitrogen. To bring them to the nominal level, and further then it is combined with the hydrogen formed in the processes and pumped through a fired heater, and that to the first reactor. So before pumping them into the reactor, into the SR reactor, what is done? The naphtha feed is firstly hydrotreated to remove the trace amount of sulfur and nitrogen present into the naphtha feed to bring them to a nominal level. Then along with this treated naphtha along with the hydrogen is pumped into a fired heater to bring it to a required temperature, and this heated feed along with heated feed mixture of naphtha and hydrogen is then fed to the first reactor. The first reactor temperature is kept in the range of 500 and the pressure is kept from 3,450 kilopascal, that is almost about 500 psig. Why this high temperature? That also I will tell. In the first reactor, the fast at endothermic naphthene dehydrogenation takes place, resulting in a drop of temperature. Okay, in a considerable drop of temperature. Okay, so in the first reactor, there are fast endothermic reactions takes place. That is the naphthene dehydrogenation to form into aromatics takes place. So there sharp drop of temperature takes place, and this is restored to the appropriate. So before sending this mm, product of the first reactor into the second reactor, the temperature, we need to increase the temperature of the feed again. So this is restored to the appropriate level through a second fired heater, and then to the before sending into the second reactor, it is again sent to a fired heater where that it gains the required temperature, and then it is sent to the second reactor where a further lesser temperature drops occur. So the more temperature drops occur in the most temperature drops occur in the first reactor. Okay, less than the second one. Okay, I mean more than the second one. The mixture then passes to a third heater and then to a third reactor where the final reaction occurs. And if sometimes we don't get the desired properties of the reformate, the desired octane number and desired yield at the end of the third reactor, then sometimes a fourth reactor is also added in the series. Okay. So this is a SR reactor process. So what happens from here? We feed is given, that is the naphtha feed, basically treated naphtha feed to remove for dehydronitrification or dehydrosulfurization is done, and it is fed from here, this treated naphtha, and it goes to a combined feed exchanger where it exchanges heat from the reformate. Okay, reformate from the final reactor. Here, three reactors are there. So the reformate from the third reactor, it goes into a combined feed exchanger where this treated naphtha, it exchanges heat from the reformate, and along with the hydrogen, this is the hydrogen, along with the hydrogen, it goes, the mixture of naphtha and hydrogen, this heated mixture of naphtha and hydrogen, it goes into the first fired heater. This is the fired heater 1, fired heater 2, fired heater 3, reactor 1, reactor 2, reactor 3. Okay. So after then this hot mixture of naphtha and hydrogen is sent to the heater where it again raises the temperature and is sent to the reactor where the endothermic reaction takes place of the conversion of naphthenes to aromatics, and further it is sent to the second heater. Product from the first reactor is sent to the second heater for gaining the temperature, and then it is further sent to the second reactor, then where reaction takes place. Further it is sent to the third heater and then third reactor for the final reaction and formation of the reformate. And from that, the reformate is given from the bottom of the third reactor, and where this further goes and exchanges heat from the feed naphtha. And further after that, this reformate is taken to a cooler where heat exchanging and further lowering of the temperature of reformate takes place, and further uh, it is sent to the separator where the hydrogen rich gases are sent above for recovery, and where some amount of hydrogen is given back to add it along with the feed here, and some is given out for the given out from the recovery section where which can be used for hydro treatment of the feed for dehydrosulfurization or dehydronitrization. So for that purpose is given out. Further after from the separator, this heavy reformer is sent to the stabilizer where this reformate is stabilized, and the from the upper head of gases are given, and then some amount of LPG is also given out, and we get the reformate, this stabilized reformate from the bottom. Okay. During the course of the reaction, coke is So during the whole reaction takes place, the coke is laid down on the catalyst, reducing its activity, and the cycle of catalyst reactivation is minimized. So this coke keeps on depositing on the catalyst. So if we do not minimize this coke deposition on the catalyst, what will happen? It will not work for 6 months also. So for some measures need to be taken so that at least some amount of coke coke can be minimized to further extend the lifetime of the one cycle of the catalyst. Okay. So the cycle of catalyst minimization is done by maintaining a high hydrogen to hydrocarbon ratio. Mainly it is maintained into the 6 to 1 ratio. So maintaining a high hydrogen to hydrocarbon ratio sometimes also helps in minimizing the coke deposition. And indication of reduced catalytic activity results in the need to raise the, and sometimes the reactor temperature is also made high to maintain the octane number of the reformate. To tackle to counteract the reduced catalytic activity, we sometimes raise the temperature also to maintain the octane number of the reformate. But qualities of the reformate is increased, but due to the increase in the temperature, quality of the reformate is increased, but at the expense of lowered yield. Okay, so eventually the loss of yield of the desired octane number reformate is such that the plant must be, so at a time will come that the yield also will yield and quality of the reformate both will not meet the required demand. So then the plant must be shut down and the catalyst must be regenerated. Okay, this could either be in situ burning. This can either be done by in situ burning, as I told in the previous in the FCC unit also, either by burning of the coke in the presence of oxygen. So what will happen? It will produce carbon dioxide and uh, carbon dioxide and will remove the coke on the surface from the surface of the catalyst. Or if the catalyst is completely exhausted, that even after the removal of the coke also there is no yield and quality of the reformate is not met, then sometimes the completely catalyst is replaced by the fresh material. Okay. Okay, so the improvement, so to tackle this problem of again and again shutting down the this reforming unit, an improvement in the SR reforming system is done, which is cyclic reforming. So along with the an extra swing reactor is kept, was introduced. What is done that when the complete exhaustion of the catalyst of the one SR reactor is done, then it is replaced by this swing reactor. This could be brought into operation with a charge of fresh or regenerated catalyst when one of the reactors needs regeneration. Okay. So it is that when the shutdown is required, we do not shut down but replace that exhausted catalyst reactor with this swing reactor. It is known that more aromatics and higher octane reformate at higher yields were produced by at lower pressure. Okay, so the lower pressure and lower severity mean good quality is meant to be produced at lower pressure and lower severity option. But if the coking of the catalyst takes place, then we need to increase the severity to limit the coking of the catalyst. So basically both the quality and coking in limitation, they counteract each other. Okay, so sometimes bimetallic catalysts were also used as acted as a improvement and enabled operation at lowered pressure of 200 to 300. Basically in the previous one we needed a pressure of 500 psig, as I told in the last slide. But if we use bimetallic catalyst, then the pressure can be lowered up to 200 to 300 psig, and to give a good octane number of 95 to 98 octane reformate and a cycle length of 1 year. And mean regeneration cycle can even extend up to 1 year. Where in the case of the single reactor, it was 8 to 12 months. 8 to 12 months, that is, it may vary. But in case in this bimetallic catalyst, it can go up to 1 year. Coming on to the continuous catalyst regeneration process. So it is basically the introduction of CCR process permits operation at a lower pressure than SR cyclic reforming process with a much lower hydrogen to hydrocarbon ratio. Why so? Because here continuous regeneration of the catalyst is taking place. So uh, uh, we do not need to shut down the reformer system after 6 months or 1 year after complete exhaustion of the catalyst, because the catalyst is regenerating after every operation. Okay, so to tackle with the coke deposition problem, we needed to increase the pressure up to like very high pressure, but that is not required here. So lower pressure can also work, and moreover, the same was done to same coking problem tackle was done by improving the hydrogen to hydrocarbon ratio. That is also not required here. Okay, the coke laid down rapidly on the catalyst is no longer a constraint in this process, as the catalyst is being continuously regenerated. In this process, the reactors are mean in the last procedure in the SR unit, the catalyst, the reactors were placed in the series order. Okay, in the series order, whereas in this case, the reactors are stacked vertically one upon another instead of side by side with catalyst moving downwards through them. Then these all the reactors are kept one above other, and the catalyst keeps moving from top to bottom, and a stream of spent catalyst is transported by hydrogen lift from the bottom reactor, and the used catalyst is transported from the bottom reactor to a regenerator system, and then back after regeneration. That catalyst is again given off from the top of the reactor. The catalyst in the reactor is therefore essentially fresh, as regeneration takes place continuously. So the catalyst is essentially fresh the whole time, and it can be operated at a pressure at a down up to 50 psig. As in the SR, it was up to 500 psig. Here it can work even up to 50 psig regardless of the coke deposition problem of the catalyst. Okay, coming on to the flow diagram here, as I told that here catalyst reactors are kept one above the other. This is as you can see, on the top of one catalyst is kept, one reactor is kept on the top of other. or okay, so we take naphtha feed from here, and here it exchanges heat from the reformate. So here this is the reformate stream. It goes into this combined feed exchanger, from where naphtha along with the hydrogen, it mixture of naphtha and hydrogen exchanges heat from the reformate, and it is then sent to the first reactor. Okay, after heat exchanging, it is sent to the first reactor, where reaction takes place further. The product from the first reactor is given to the heat for it goes for the heat exchanger for exchanging heat and send into the second reactor. Bottom from the second reactor is further sent for the heat exchanging and send into the top of the third reactor. Likewise, it goes to the fourth reactor, and from below we get the spent catalyst, which is the exhausted catalyst. It is sent to the regeneration catalyst chamber, where the regeneration of the catalyst takes place, and from the top the spent catalyst is enter, and from the bottom regenerated catalyst is given off back into the top of the CCR reactor. Okay, and the reformate, it goes from here into after the heat exchanging, it is given off to the uh, separator, where from the above hydrogen rich gas is taken off, and it is further separated and stripped off from the unwanted products, and some amount of hydrogen is given back into the heat into the feed for a reforming procedure, and remaining it can go for the treatment of the naphtha. And further this reformate is taken into the stabilizer, where from below we get the stabilized reformate, and from above of gases are given. The difference between SR and CCR process is that the selectivity towards aromatics is more important in CCR process than SR. So basically, the selectivity basically means that as the catalyst is regenerated after every time, so the we get better yields and better quality reformate in CCR. So basically, the selectivity towards aromatics, as aromatics provide much better octane number. So the selectivity of CCR procedure toward aromatics is more in case of CCR than SR. Tolerance of high coke deposition of the catalyst is one of the prime factors. As the regeneration cycle is much more higher than that of the CCR. So the catalyst used in the SR reactors, basically the semi-regenerative cycles, the catalyst in those cases have a very high tolerance power. They have mean more robust catalysts are used in case of SR because they need to tackle with the high coke deposition problem. So they need to be more sturdy and robust in respect in relative to the catalyst used in the regeneration catalyst used in the CCR unit. Okay. Coming on to the feed and process variables, naphtha feed is generally it is taken in the boiling range of 80 to 85 degrees C. Okay, and it should be C5, C6 hydrocarbons are excluded from the feed, and moreover C7 paraffins boiling up to 90 degree are also excluded from the naphtha feed. Why so? Because these C5, C6, C7 feeds they act as the benzene precursors, and we discussed earlier, they are very toxic in nature. This is carcinogenic. Benzene is carcinogenic. So that is why these C6, C5, C5, C6, C7 cuts, they are avoided are excluded from the feed so that no amount of benzene is released into the atmosphere as this is carcinogenic in nature. Okay. And this feed boiling range is from 80 to 50, whereas in the case of reformate, it as we get hot reformate after the reforming procedure, so it may vary up to 210 degrees C boiling point. Okay. Reactor temperature, the primary control for product quality in catalytic reforming is the catalyst temperature, which can be adjusted by heater outlet temperature. So the catalyst temperature should be adjusted for accordingly to maintain the product quality. Okay, and the SR unit operates this in the 490 to 525 range, whereas CCR it operates at a higher temperature of 525 to 540 degrees C. Okay. Velocity is basically indication of the contact time of feed and catalyst. So it is expressed as the liquid hourly space velocity, which is LHVC, which is LHSV, which is the volume of the naphtha charge per hour per volume of the catalyst. So a space velocity of 2 per hour is typically required. Coming on to the hydrogen to hydrocarbon ratio, as we discussed, this is the ratio of moles of hydrogens in the recycled gas to moles of naphtha charged to the unit. So, as we discussed, due to the coke deposition problem can be limited in the case of SR by taking more higher hydrogen to hydrocarbon ratio. So, in the case of SR, hydrogen to hydrocarbon ratio is more compared to CCR, which is 8 to 1 ratio. 8 ratio 1, whereas in the case of CCR, it may decrease up to 1.6 ratio 1. And due to there is no problem of coke deposition in the case of CCR system. Okay. Catalysts used, the reforming catalysts are composed of base supportive material alumina, which on which typical which on which catalytically active metals at least at less than 1 weight% are evenly distributed. Why less than 1 weight% because they are very expensive. So these active materials are used in a very less amount, and not only expensive, they are highly active also. So smaller amount works for the very good results. Okay. So monometallic catalyst, so platinum is the active material, and if bimetallic along with the platinum, rhenium is normally added for a more severe processing requirement. Okay. One bimetallic catalyst is used, which is 0.35 weight% of platinum and 0.4% rhenium. Okay, rhenium. A special requirement occasioned by the introduction of CCR process was the necessity for the catalyst to be resistant to occlusion. Okay, so in the case of CCR process, as we know that it is a vertical reactor, so the catalyst falls from the top to the bottom, so it needs to be resistant to attrition. Mainly when the catalyst falls from the top of the reactor, it may break by collision with each other. So a mechanically strong spherical catalyst is used in place of the more conventional cylindrical extrudates. Why? Because cylindrical catalyst particles, they have edges, so they are more prone to attrition. Whereas if we use spherical catalyst, they do not have any sharp edges, so they are not they are resistant to attrition. Okay. An innovation whereby two different catalysts are used in the same SR plant, exploiting the better features of sometimes a mixture of two or more than two types of catalysts are also used, and it is known as staged loading. So basically, as we know that the CCR catalyst, it has different catalysts, four catalysts in series, one above the other. So the first, sometimes more than one type of catalyst can be used. The first catalyst is loaded in the first and second reactor, where the principal reactions are dehydrogenation of naphthalene and dehydrocyclization of long chain paraffins. These reactions have high rates and results in relatively little coke in the catalyst. Okay, and here the catalyst is used which exhibit high selectivity to here in the first two reactors mainly conversion of naphthenes to aromatics, and uh, dehydrocyclization basically is the uh, production of isoparaffins or some smaller paraffins takes place. So for these reactions they have high rates and little coke deposition takes place. So the catalysts which have good selectivity for aromatics and low selectivity to cracking on conversion of naphthenes and paraffins. Such catalyst is used in the first two reactor, whereas in the last reactor, short chain paraffins are dehydrocyclized to aromatics, and cracked products require higher temperature. So for higher temperature, they result in higher coke formation on the coke, and so catalyst with high activity and stability is required. Okay, coming on to the isomerization of naphtha fraction. So, virgin light straight naphtha typically which boils in the range of 30 to 75 degree, consisting of C5 to C7 cuts, C5 to C7 paraffinic hydrocarbons with possibly some cyclic, sometimes cyclic structure like cyclopentane or methyl cyclopentane are used as the feed. It can be seen that the branched chain isomers of N-paraffins have much higher octane number than the N-paraffins. As I told that the isoparaffins and aromatics are required for good octane number. So N-paraffins, these isoparaffins are the branch chain structures of these N-paraffins. Basically, the branch chain isomers of N-paraffins. So they have better octane number compared to N-paraffins. So what we do, we convert these N-paraffins into, we isomerize them and convert into their isoparaffin structures. Okay. So the greater the degree of branching, great higher is the octane number. Isomerization process is designed to increase the proportion of branch chain paraffins that exist naturally in light straight run naphtha, and so basically, its aim is to increase the proportion of branched chain paraffins in comparison to the N paraffins to increase the octane number. Okay. In more advanced processes, the aim is to increase the content of highly branched paraffins and eliminate N paraffins entirely. Okay. It is noted that the sensitivity of paraffins is a very low compared with that of the cyclic compounds. Okay. So basically, here sensitivity is research octane number minus motor octane number. Okay. So research octane number and motor octane number, as I explained earlier, this motor octane number, it is basically octane knocking property under load, under more robust environment, which automatically reduces the octane number in under, I mean, compared to research octane number, which is the octane number measurement at normal conditions. Okay. So the sensitivity of paraffins, where basically the difference of research octane number and motor octane number of paraffins is very low compared to the cyclic compounds. Okay. More sensitivity means the more difference of research octane number and motor octane number. Basically, if both are very close, then it is a very good quality product. Basically, that means under load also it has a good motor octane number similar to research octane number. Research octane number, we can say that the octane number at ideal conditions, mean at normal conditions, whereas in motor octane number, it is the octane number at extreme conditions. So if both are similar, then that means it has a very good quality. It is a very good quality fuel. So that's why here we can see that the sensitivity, the difference of these two in case of paraffins is very low, very low. Just a second. Sorry for that. Basically, the sensitivity of paraffins is low. That is the difference of research octane number and motor octane number is very low in case of paraffins as compared to the cyclic compounds. Since the two main components of gasoline pool, the main components of gasoline pool are catalytic cracked gasoline and catalytic reformate have much higher sensitivity. This makes isomerate a valuable component in the pool. Okay. So isomerization of the N-paraffins, isomerates, they also act as very good addition to the gasoline pool. It is observed that all the isoparaffins boil at a lower temperature than the corresponding N-paraffins. These isoparaffins have lesser boiling point compared to the N-paraffins. This is reflected in an increase, which means that the isoparaffins have more read vapor pressure compared to the N-paraffins, which means that there is an increase in the read vapor pressure on isomerization, which must be allowed for the subsequent gasoline blending operation. Okay. So in the starting, as I told, that butane is sometimes added to maintain the read vapor pressure of the gasoline. So instead of that butane, using that butane sometimes by these isomerates can also act as the these act as agents to increase the to maintain the read vapor pressure. So instead of butane, we can also blend these isomerates in gasoline pool. Okay. The procedure, which is the isomerization process, it is simplest form of process consisting of passing the light sweet run naphtha over a suitable catalyst in an atmosphere of hydrogen under temperature and pressure condition appropriate to the catalyst. Okay, we simply pass the naphtha and hydrogen mixture over a suitable catalyst and isomerization takes place. Is so basically isomerization is favored at low temperatures. So, for example, for pentane isomerization, during the isomerization of pentane, equilibrium mixture of N-pentane and isopentane forms, which is almost 80% isoparaffin at isopentane at 300 degrees C. And if we slightly decrease, if we decrease the temperature from 300 to 100 degrees C, this yield is slightly increased from 80 degree to 85 degrees C. Okay. Here also we can see, for example, this is a mixture of 2-methylpentane, reaction of 2-methylpentane and 3-methylpentane, producing which is an octane number of 75. It produces 2,2-dimethylbutane and N-hexane. So this N-hexane, it has a research octane number of 25 and this has a research octane number of 7. Just a second. This is not given, but it has a higher octane number than this 25. Okay, so here we can see as the temperature is lower, the yield of this higher octane number product is higher here in lesser temperature, whereas at the increased temperature the yield of this higher octane number product decreases, whereas the yield of the lower octane number product increases. Okay, thus for isomerization of C5C6 mixture as in LSR naphtha, there is a positive advantage in operating at lower temperature and catalyst development has been oriented in that way. Coming on to the what kind of catalysts are used for isomerization, two different types of catalysts are used. One is a platinum bearing zeolite, which requires an operating temperature of around 260 degrees C and operating pressure of 260 to 500 PSIG. Whereas the another type is amorphous platinum bearing chlorided alumina, which is operating at lower temperature of 120 to 180 degrees C. Favors the formation of more branched isomers. Okay, but here addition of organic chlorides for activation, continuous addition of organic chlorides for activation of this catalyst takes place. Okay, there is also a third type of catalyst which is platinum unsulfated metal oxide, which works at a moderate temperature between the above two catalysts. Okay, the increase in the research octane number of 68 to 70 light straighter naphtha typically up to goes up to 78 to 80 for zeolite catalyst and 82 to 80 for amorphous catalyst. Okay. Coming on to the another procedure which is alkylation. It is also act, these alkylates also act as very important addition to the gasoline pool. Why? So in alkylation procedure, the light olefins, typically propylene and butylene, are combined with isobutane to form branched chain isoparaffins of higher octane number. Okay. So propylene and butylene, these two we get from the FCC unit. For the reaction of propylene and butylene, where do we get this propylene, butylene, and this isobutyl? Okay, so propylene, butylene we get from the FCC unit, and isobutane we get from, also we can get from FCC unit also, catalytic reformer unit, or crude oil distillation unit also. So the catalyst used here is H2SO4, or I mean sulfuric acid or hydrofluoric acid, and the alkylates are valued components of gasoline on account of their high octane number and low sensitivity. Okay. So this alkylate is the third largest component after catalytic crack naphtha and catalytic reformate in the gasoline pool. Okay. Coming on to the process chemistry of the alkylation, primary reaction of alkylation are the reactions between isobutane and C3C4 olefins. Okay, the reaction between isobutane and propylene is to produce 2,3-dimethyl pentane, which gives a research octane number of 89. And the reaction between isobutylene and isobutane yields 2 to 4 trimethyl pentane or isooctane, which is the standard for measuring the octane number of a fuel. Okay. So the 1 butane and 2 butane, sometimes 1 butane and 2 butane also it reacts with isobutane to form branch chain dimethyl hexane, which gives a research octane number of 79, and isomers of trimethyl pentane, which gives a research octane number from 96 to 100. Okay. Some other secondary reactions are also there in this alkylation procedure. So the secondary reactions are isomerization of 1 butane and 2 butane. So this is the isomerization of 1 butane, then polymerization reaction which produce heavier paraffins with reduced octane number. This is not a desirable reaction. Cracking disproportion, cracking of larger polymer molecules to smaller fractions, which further this is a complex reaction. Firstly, cracking of the polymerization reaction to smaller fragments take place. Further, the smaller fragments they join and react together to alkylate. Okay, to form alkylates. Then hydrogen transfer reaction between propylene and isobutane produces butylene and propane. Okay. Coming on to another procedure which is polymerization. So this process it starts with the C3 and C4 olefinic streams, which we get from the thermal or catalytic cracking, and it polymerizes to form C6, C7, or C8 olefins in the gasoline boiling range. Okay. So the process is called oligomerization. Basically, it is called oligomerization rather than polymerization. Why? So oligomerization is the forming of units up to 8. So C8. Okay. So it is mainly oligomerization rather than calling it polymerization, and it is also called as catalytic condensation. However, the product from this polymerization, it is always called as polygasoline, and there are two types of process operations. The major one is the UOP, catalytic condensation process, which is based on a solid catalyst and can be applied to polymerize C3 C4 olefins into a jet fuel or diesel oil boiling range. So it is done on a solid based catalyst, and it can be used to polymerize C3 C4 olefins to produce cuts into the jet fuel or diesel oil boiling range. Okay, and the other procedure involves known as dimersol, is based on a consumable liquid phase catalyst, and this process consists of polymerization of C3 olefins to form dimeres. Basically, C3 reacts with C3 to form dimeres, which is called hexane for gasoline blending. Another procedure, another thing is the benzene reduction. So as I told, benzene is carcinogenic in nature. So if we are dealing with C6 cuts, then if some amount of C6 cuts are present in the gasoline, then during the combustion of the gasoline in the motor engine, it may emit out, it may release benzene in the emission gases in the in the exhaust. So this needs to be controlled, is the most important parameter to control toxic emissions. The major source of benzene in the gasoline pool is catalytic reformate, which typically contributes to 50 to 75% of the pool. So mainly this catalytic reformate, it may consist of a benzene portion. And so what we do, the two basic approaches is to remove the benzene precursors before reforming procedure only, to remove the benzene from the precursor itself, or to fractionate, or if there is some benzene present in the reformate also, then to fractionate, then to do the distillation of this reformate to remove the benzene rich light for reformate stream for subsequent benzene conversion or extraction. Coming on to another type, another procedure, which is the solvent deasphalting. So solvent deasphalting, just a second. So what is next thing after reforming is the solvent deasphalting. So solvent deasphalting, it is a very it is a physical separation process employed to remove asphalts from the vacuum residue. So basically, what is asphalts? They are mainly mm, asphalts are mainly heavy long chain saturated hydrocarbons, mainly N paraffins. Long chain heavy, not N paraffins. Basically, they are long chain hydrocarbons, mainly long chain polymer hydrocarbons, rich in carbon content, very rich in carbon content, and they are very heavier compounds which are present in the heavier residues. Okay, so we need to remove these asphalts from the these are basically condensed or polymerized hydrocarbons which are present in the heavier residue, mainly in the atmospheric distillation unit, vacuum distillation unit. These asphalts may be present, which may lead to the corrosion of the engine, or during many applications it may lead to corrosion, or reduce the property of the fuel, or deposition of the asphalt also will take place. Okay, so solvent deasphalting needs to be done, that is the physical separation of asphalt from the vacuum residue. It is mainly present in the vacuum residue. Okay, so typical usage for the deasphalted oil product includes lube bright stock, lube hydrocracker, or feed, fuel hydrocracker feed, and fluid catalytic cracker feed or fuel oil blending. So mainly this, after these deasphalting, we what we get, the oil we get, we call it the deasphalted oil. Mean the after the oil, after removal of the asphalt content from it, it is called the deasphalted oil. It is mainly used in the product. It includes it is mainly used as lube bright stock. Lube bright stock is basically the vacuum residue, lube bearing vacuum residue. When it is the asphalt content is removed from it using a solvent, then it is called as the lube bright stock. Then lube hydrocracker feed. This deasphalted oil, lube bearing deasphalted oil, it can be set for the hydrocracker. Then fuel, the diesel fuel, the basically vacuum residue which is not consisting of lube, not lube bearing vacuum residue. It is the fuel bearing vacuum residue. Then after removing the asphalt from it, it may be sent to the hydrocracker feed. Then it can be used for fuel oil blending also, and fuel catalytic cracking also. Okay, so depending on the operation, the asphaltene products may be suitable for use as a blending component for various grades of asphalts, as a fuel oil blending component, or as a feedstock to a heavy oil conversion unit such as coker or residue hydrocracker. Okay, this solvent deasphalting process is flexible enough to enable the processing of both long and short residue. Long residue, basically atmospheric distillation, atmospheric residue, and short residue is the vacuum residue. Okay, So the process involves the solvent deasphalting process. It is an extraction process where the charge is separated by solubility of more desirable deasphalted oil and less desirable asphaltene material by a solvent. So simply what is done, charge is mainly feed, that is basically vacuum residue or atmospheric residue or any kind of heavy residue which consists of asphalt. Okay, so this is the charge. It is made soluble into a suitable solvent. What will happen? The solvent will dissolve the oil content in the heavy residue part and will leave out the asphaltene material at the bottom. Okay, so that's how we remove the asphaltene from the in the de-asphalting procedure. Typically, light paraffinic solvents are used mainly such as propane, isobutane, butane, and pentene are used in the solvent de-asphalting process. The solvent composition, then operating temperature, then solvent to oil ratio are basically the main factors are selected to achieve the desired split between the light deasphalting oil and heavy asphaltene product. The solvent most often used for production of lube oil by bright stock is propane or a blend of propane and isobutane. Okay. For application where deasphalting oil is sent to conversion processes such as FCC, the solvent is more likely to be butane and pentane or a mixture of two. And if this deasphalting oil, if this deasphalted oil is used in as the lube oil bright stock, then the solvent used is propane or isobutane. And if it is used for conversion, if it is used as a feed for conversion in FCC, then a mixture of butane or pentane or both or single butane or pentane is used. Okay. The process variable, coming on to the process variables of the solvent deasphalting procedure, at properly selected pressure and solvent to feed ratio, the separation of asphaltic constituents is possible at the temperature range of 40 to 90 degrees C. Okay. For the maximum extraction of valuable hydrocarbons from the feed, the temperature in the extractor is maintained at 550 to 65 degrees C, and at the bottom, it is 75 to 80 degrees C at the top. Okay. So in the extractor unit, at the bottom temperature is made less, is kept less, that is 50 to 65, and at the top it is made higher, that is 75 to 85 degrees C, and propane is mainly used as solvent. This temperature difference in the extractor is obtained by heating of oil solvent mixture by means of steam coils at the top of the extractor. At high temperature with the same solvent to feed ratio, asphaltic constituents pass easily into the lower layer. So what happens at the high temperature, the asphaltic constituents, it easily passes into the lower layer, which improves the color of it easily settles down. The asphaltic content at high temperature easily settles down. Thus, it improves the color of the deasphalted oil and lowers its viscosity, density, and coking ability, but also lowers the yield of deasphalted oil. Okay. So the pressure in the extractor is maintained at a level of 3.5 to 4 megapascal depending on the extraction temperature. Solvent to feed ratio is determined by the nature of the feedstock and the temperature of the asphalting. This ratio is lower at a higher concentration of asphaltene, mean the solvent to feed ratio is lower at a higher concentration of asphaltene in the feedstock and vice versa. Mean basically if there is higher concentration of asphaltene, mean if the feed consists of very large amount of asphaltene and oil content is less, then we need to take small amount of solvent. The amount of solvent depends on the amount of oil present in the heavy residue. Okay, if the asphaltenes are less but the oil content is very large in that residue, then to dissolve that large amount of oil in the solvent, we need more solvent. So the solvent to feed ratio is taken more. Okay, so the yield of desalted oil can be increased by increasing the solvent to feed ratio under a given set of operating conditions. As the yield is increased beyond a certain range, the Mean if the yield is increased beyond a certain range, then the metal content of the deasphalted oil increase very rapidly, while the removal of sulfur and nitrogen is not significantly affected. The deasphalted oil produced for lubricant end use must contain significantly less asphaltenes than a similar deasphalted oil produced for fuel and usage. Okay. If the deasphalted oil, mean the oil after removal of the asphaltenes, it is need to be used as in the lubricant application, then the asphaltene content should be very less in compared to, mean after the removal of the asphaltenes there can be some traces of asphaltene still left, so that traces should be very less in case of lubricants, whereas if it is used in the fuel and usage, then the it can be more than the lubricant. Coming on to the next procedure, which is the base oil manufacturing process. Basically, it is the lube oil manufacturing process. Okay, so the majority of lubricant for base oil production continues to originate in vacuum distillates. Okay, as we know that the vacuum distillation unit side cuts, they mainly consist of the uh, uh, vac mean they mainly consist of the lube oil base stock. Okay, base oil stock, mainly lube oils. Okay, lube oil cuts, vacuum gas. So the manufacturing route, it consists of some of the basic steps, that is vacuum distillation to produce distillate feedstocks. The vacuum distillation which produces with distillate feedstocks from the side cuts. Solvent deasphalting to produce heavy lubricant base oils from mean these distillate feedstocks, mean vacuum gas oil, heavy vacuum gas oil, light vacuum gas oils, they are removed from the vacuum distillation. Then further the lubricant heavy lubricant base oil, it is solvent deasphalting is done of the vacuum residue. Mean the vacuum residue is dissolved into a suitable solvent to remove the asphaltene compounds from the vacuum residue to produce the heavy lubricant base oil. Okay. Then solvent extraction of the vacuum distillates to improve quality. Vacuum distillates, solvent extraction of the vacuum distillates is done to improve the quality such as viscosity index and saturates content to by removal of undesirable components. And solvent or catalytic dewaxing, then some amount of wax contents are also present in the vacuum residue. Oh, then those solvent or catalytic dewaxing is done to remove the wax and improve the low temperature properties, mainly the viscosity index or pour point, to improve the these two qualities. Dewaxing is done. Solvent dewaxing is dewaxing done using solvent, and catalytic dewaxing, in this the wax is not removed. Instead, that wax content, that is N-paraffin contents, are converted into isoparaffins, thus improving the uh, low temperature property as well as the uh, improve the octane number. Then clay or hydrogen finishing is done to improve the color stability of the lubricant based oil products, and severe hydrotreating process to improve viscosity index and saturate contents. Coming on to the lube deasphalting, the heaviest lubricant base oils are contained in vacuum residue and thus cannot be recovered economically by distillation. Okay, we cannot extract the lubricant oils from the vacuum residue by distillation, because why so? Because we need to provide the vacuum, and huge amount of energy is required in that, which becomes which is not feasible. So instead of that, lube deasphalting is done. So most frequently used process for recovering the heavy lube molecules from the semi-solid asphalts and resins contained in the vacuum residue is propane deasphalting. So propane deasphalting, it is an extractive precipitation process. What happens is that we take this vacuum residue. The process uses the density difference and inverse solubility characteristics of light liquid hydrocarbon solvent to selectively precipitate out asphalts, resins, metals, and other hydrocarbons. So what happens is we dissolve this vacuum residue in propane. So this propane extracts this heavy lube base oil with it precipitating out the asphalts, resins, and metal and other hydrocarbon content below. Okay, so the deasphalted oil produced is suitable for further refining into heavy lubricant base oil. Okay, so when we receive this deasphalted oil, it consists of both lubricant base oil as well as propane, and it is further refined to produce to remove the propane as well as to give the heavy lubricant base stock. Okay, coming on to solvent extraction process, the purpose of solvent extraction is to prevent corrosion, protect catalysts in subsequent processes, and improve finished products by removing unsaturated aromatic hydrocarbons from lubricant stocks. Okay, the solvent extraction process separates. Mean in the lubricant stock, there are these components present: aromatics, naphthenes, and impurities. But in the case of lubricants, we need to remove these unsaturated aromatic hydrocarbons. Okay, so the solvent extraction process, it separates these aromatics, naphthenes, and impurities from the product stream by dissolving or precipitating. And the feedstock is first feedstock, it is dried and then it is treated using a continuous counter current solvent treatment method. Mean the dried feedstock, it is treated with the suitable solvent in counter current operation. The solvent is separated from the product stream by heating operation, and when the this oil, this lubricant, it completely dissolves with the solvent, leaving out the impurities behind. We need to separate the solvent from the product stream by heating, evaporation, or fractionation, or residual traces are subsequently removed from the raffinate by steam. And sometimes, if there is very small traces of solvent present, then it is separated by steam stripping or vacuum flash. The quality required in a lubricating base stock are usually determined by measurement of either the product viscosity index or saturated content. Okay, saturate content. To reach required viscosity index of saturates level, it is necessary to remove aromatic compounds. Saturates level basically means requirement of N paraffins is there, and viscosity index, that means 4 points need to be maintained. Okay, why 4 point needs to be maintained? For the transportation from hot area to colder region, 4 point needs to be maintained as we discussed earlier. Okay, so the solvent suitable for this is for that purpose we need to remove aromatic compounds. The solvent suitable for this aim must be selective in removing predominantly aromatics. And so what we need to do, we need to select suitable solvent so that it removes aromatics as well as selectively removes sulfur, nitrogen, and oxygen compounds also without affecting the saturates level. Okay, so the three main solvents are furfural, phenol, and N-methyl 2-pyrrolidone, which is NMP. Other less frequently used solvents are liquid sulfur dioxide, nitrobenzene, or 2,2-dichloroethyl ether. Okay. The selection of specific processes and chemical agents depends on the nature of the feedstock. The selection parameters are the nature of the feedstock being treated, then the contaminants present, and the finished product quality. Then after the solvent extraction, what we need to do, we need to remove the solvent. Also, we need to regain our solvent. So for that purpose, three solvents, mainly furfural, phenol, and NMP is used. So their extraction procedure also we need to do. So firstly, coming to the furfural extraction, furfural refining has been one of the most widely used process for lubricant base oil production worldwide. The main extraction process variable used are temperature, treat ratio, and amount of extracted material recycled to the feed. Treat ratio, basically it is the solvent to feed ratio. Okay. Typically, temperature in solvent dose lies in the range of 40 to 120 degrees C and 100 to 250% on feed respectively. Okay. Extraction device currently in use are rotating disc contractors and packed or tray towers and centrifuges. Feedstocks are counter currently using essential anhydrous solvent. And hydrosolvent, that means furfural, should be dried. It should not consist of any moisture, and furfural preferentially extracts aromatics and compounds containing sulfur, oxygen, and nitrogen. Okay. Coming on to the another procedure, which is the phenol extraction. Phenol exhibits good selectivity as a lube oil extraction solvent. But as we used dried furfural, but in the case of phenol, water is required. Water is used as a treating solvent as it acts as a solubility modifier or anti-solvent, and it is used to balance solvent treat rate with treater operating temperatures. Okay, so extractor can be a mixer settler. The main disadvantage in using phenol is that it is phenol is highly toxic in nature. Okay, the proper protective measures should be taken in operation, plant shutdown, and maintenance also difficult and time consuming. Coming on to the yield of refined oil is usually sometimes somewhat lower with mean the yield of the refined oil that we get, it is somewhat lower with in case of furfural than that obtained with it is usually lower in the case of phenol than that obtained with the furfural and NMP. Finally, coming on to the NMP extraction, why NMP? It is non-toxic in nature. It is high it has very high good solvent power, good selectivity, and it also have a very high boiling point. So the loss of the solvent problem is also solved. It acts as a very attractive alternative to phenol. The process is best in the areas of solvent circulation, and it requires less corrosion protection, which results in the lower requirements in energy, investment, and operating cost. Okay. The operation is done in a mixer settler with 15 to 20 trays. And the higher boiling point of NMP results in more efficient heat integration and the faster settling and coalescing characteristics due to lower solvent viscosity results in a higher treat capacity. The lower solvent losses make reduce makeup solvent purchases and hence production cost. As I told, it has very high boiling point, so solvent losses are also maintained. Coming on to the next procedure, which is the solvent dewaxing. As I told, the petroleum products, all the crude oil, it consists of uniform distribution of waxes are there. So what are waxes? They are solid hydrocarbons which melt in the range of 35 to 95 degrees C, which are soluble in all crude oils and their fractions. So they are uniformly distributed throughout the crude oil and all the distillate fractions. So it is very difficult. Mean they have a boiling range in the range of all the distillate fractions and the lubricating oils as well. So therefore, it is very difficult to remove wax content through distillation. Okay. They boil in the wide temperature range of distillate fuels and lubricating oils and hence cannot be separated by distillation. On the other hand, the dissolved waxes precipitate out at lower temperature, thereby the wax bearing diesel fuel and lubricating oils must be dewaxed. So why we need to dewax? What is the problem? The problem with with the wax content in the fuel is that when we transport this fuel from a higher temperature area to lower temperature area, what will happen these waxes will start to crystallize in the fuel pipeline, thus crystallizing and solidifying, thus hampering with the flow of the diesel fuel. Okay, so that is why we need to remove this wax content from the fuel. Wax is a valuable and moreover it is not a very bad problem. It is not a very crucial problem. It is a crucial problem to remove wax, but this wax, it is a very valuable byproduct as it is used in various applications. Okay, so dewaxing is done by chilling the oil and when wax crystallizes out. So simplest method to remove the wax on dewaxing is what we do. We simply freeze the crude oil or the distillate fraction and the crystals of the wax comes out. And we simply filtrate it or centrifuge it or settle it down. Okay. But problems with the simplest procedure are there. Okay. We'll be talking further about it. There are several processes in use for solvent dewaxing, but all of them have some general steps. Some general steps are mixing the feedstock with a solvent. We will firstly mix the feedstock with some solvent, then precipitating the wax from the mixture by chilling. We will mix it with a solvent, then decrease the temperature, chilling will be done, then crystallization of the wax will be done. Then after the crystallization of the wax filtration and all, recovering the solvent from the wax and dewaxed oil for recycling by distillation and steam stripping. Okay. There is another method there is also another method of dewaxing with urea, which is based on the fact that urea forms solid filtrable complexes, which are called adducts with large paraffins having little or no branching. So if we use urea for dewaxing, what happens? This urea along with the wax wax present in the crude oil, it forms solid filtrable complexes which are called adducts. So we can simply remove them by filtration. Okay, urea dewaxing is a very efficient, very effective on lighter stocks. Three dewaxing processes are present worldwide. The first one is ketone dewaxing, then propane dewaxing, and then catalytic hydro dewaxing. Okay, so this ketone dewaxing and propane dewaxing, these are the physical separation methods, physical dewaxing methods. But this is the chemical dewaxing method. What does that mean? We will be talking further. Or let me tell you, in the physical dewaxing, we simply crystallize out the wax and separate it by filtration. Okay, filtration or centrifugation, etc. Okay. Whereas in the chemical dewaxing, what we do, we either break down long N paraffins, mainly waxes, into useful distillate fractions or isomerize them to isoparaffins, which aid in 4-point reduction. So ketone dewaxing, typically it uses a mixture of two solvents, okay? Methyl ethyl ketone along with methyl isobutyl ketone or toluene. Why so? Uh, if we use two solvent, then optimization of the solvent component, that which solvent to use, how much is that optimization needs to be done. Okay. So this MEK component, it is an anti-solvent to wax. Whereas this is a solvent to wax. So if we add mixture of two solvents, what will happen? So, wax will dissolve in toluene and the oil will dissolve in MEK, and then the freezing will be done. MEK in the solvent mixture act as an anti-solvent for wax molecule, promoting their precipitation as crystals from the feedstock. Just a second. Okay. However, so why do we use two solvents? Why we cannot use one solvent? What will happen is, what we do, we use a mixture of two solvents. Then the one solvent will dissolve wax in it, and other solvent will dissolve the oil in it. And then we will chill this mixture, chill out this mixture, and then the crystals will form. Crystals of wax will form in one solvent, and we will simply extract it out. Okay. So why don't we use simply one mixture? Okay. Why don't we use simply one anti-solvent that will dissolve the oil along with it and will leave out the wax? Okay, why so? Because if we use MEK alone, what will happen? The oil in feed solution becomes, if we suppose use only MEK, that will dissolve oil in it. And after chilling out, what will happen? That the solubility of oil in this MEK will start to decrease. So some amount of feed oil, some amount of oil will start to precipitate out. It becomes immiscible. So, uh, so some amount of oil will precipitate out will precipitate out of the MEK solvent, and due to the decrease in the temperature, this oil will become highly viscous and will get trapped along with the wax crystals. Okay. The oil in feed solution becomes immiscible when the feed solution temperature is reduced to that required for filtration. Okay. Two phases are formed, an oil rich phase and a solvent rich phase. A solvent rich phase will be there in which the MEK along with some amount of oil will be there, whereas a viscous phase that has precipitated out from the solvent due to the decrease in the temperature, that is the oil rich phase will be there. Oil rich phase contains high viscosity index oil molecules, and due to their higher viscosity, it gets trapped in the wax cake. Okay. This results in the loss of both dewaxed oil yield and quality. Okay, so what will happen? This large amount of oil, it will get trapped into the wax cake, and if we remove the cake along with that, then we will lose a large amount of our refined oil. Okay, so to avoid this problem, a second solvent is added to MEK to improve oil solubility at filtration temperature. Most frequently used component are MIBK and toluene. Coming on to the propane dewaxing can be applied to any petroleum fraction but is particularly good for dewaxing bright stock, light, and heavy diesel fuel. Okay. One of the most important feature of the process is that it uses both propane because the propane it acts both as diluent and refrigerant. Because what will happen here, this propane it will uh, uh, act as both diluent as well as the refrigerant. It is a semi-batch process using two parallel batch chiller vessels alternatively in sequence. Another important factor is that the process will not perform satisfactorily without the use of wax crystal nucleation. In the case of this propane, what will happen? We need to add some dewaxing aids. That is, dewaxing aid is basically a crystal, a wax crystal needs to be introduced into the solution, which will act as which will aid in the nucleation as well as the grain growth of the crystals. Furthermore, a dewaxed oil product 4 point from propane dewaxing plants are limited to a lower temperature of minus 15. Mean after the dewaxing of the oil from the propane dewaxing method, the oil that we get, it has a 4 point of around minus 15, which is very good because the 4 point needs to be very low to transport the oil from a higher hotter region to a colder region. The capital cost of the plant is significantly below that of the ketone dewaxer. Why so? Because this act as both, there is less use of energy here because this propane both it does not simply act as the solvent but also act as the refrigerant. Okay. So for the chilling also we do not need extra uh, energy. Coming on to the next procedure, which is the third type, which is the catalytic hydrodewaxing process. Catalytic hydrodewaxing process has been alternative to solvent dewaxing in the manufacturing of lubricant oil-based stocks. Okay, it utilizes fixed bed hydroprocessing technology to selectively crack long chain paraffin wax into lighter petroleum gases, naphtha or kerosene. As I told, it cracks down paraffin wax molecules into lighter distillate fractions, that is lighter petroleum gases or naphtha or kerosene. Alternatively, some of the wax molecules can be polymerized to form low pore point isoparaffins. it will crack some amount to form lower light distillates, and also will crack down to isomerize some of the and paraffins to form isoparaffins, which lowers down the pour point. Okay, so recent catalytic dewaxing process combine wax cracking as well as wax isomerization. This process utilizes proprietary catalyst, which is basically the licensed catalyst to carry out the dual function, both cracking of some of the wax to lighter products and isomerization of the rest to low pour point isoparaffins. This both the procedures are done into a single reactor. Okay. Some of the other dewaxing processes involve the DMI process, which uses a mixture of dichloroethane, from where Di comes, and methyl dichloride, where Me comes. It acts as a dewaxing solvent. It is used in the production of lubricant, base oil, and low oil content waxes. The urea dewaxing process is capable of producing low pour point oils or low oil content waxes from paraffinic feedstock. So this is not a solvent dewaxing procedure. It is an occlusion process basically. What happens? The hexagonal crystalline structure of urea, it traps down the end paraffins of the six or more carbon. It traps this hexagonal structure of urea. It traps the wax molecules in the end paraffins or some branched paraffin molecules in between these hexagonal crystalline structures of urea, thus separating out the and thus increasing the crystalline structure. The size of the urea crystal keeps on increasing to remove the wax content from the oil. Okay, while percolating feed through a bed of urea, the process requires an activator solvent. uh, when we pass the feed from on a bed of urea, an activator catalyst is also solvent is required, which is mainly alcohol is used, ketone is used, or chlorinated hydrocarbons are used. Okay, coming on to the de-oiling procedure. So during the dewaxing, the wax that we get out after dewaxing, in that some amount of trapped oil is always present. So large quantity of oil is left in the crude waxes produced in dewaxing process. The oil content maybe, if we use the simplest procedure, simply by freezing the crude oil. If we do that simplest procedure, then the oil content gets trapped into the wax, it may rise as high as 50%. And if chilling is done without solvent, hence the importance of de-oiling procedure is very much. Okay, the finished wax should not contain more than 0.5% oil. So we need to decrease from 50% to 0.5%. Okay, there are three types of de-oiling procedures, mainly sweating, resetting, and solvent extraction. Coming on to the sweating procedure, what happens? A crude wax, which is mainly called the slack wax, is melted and cast into thick sheets. We take the crude wax and we melt it and form them into thick sheets, and these sheets are then subjected to slow heating on pans with perforated false bottom. Okay, as the temperature rises, this mixture of oil and wax, which is the slack wax, this sheet of slack wax, it starts to melt, and a mixture of oil and low melting wax drains out, and the heat is continued until the remaining wax has the desired melting point. Okay, the sweeting process may be repeated for the production of good quality wax. In the resettling process, what happens is the slack wax is diluted with cold naphtha. This melted portion, it is then diluted with cold naphtha and recrystallized by chilling, and the final separation of the wax crystal is done and the chilling is done. The uh, oil gets dissolved with the comes with the cold naphtha fraction, and the chilling of the wax crystal form the wax crystal, which are then separated by centrifugation. Okay, the propane or a mixture of methyl ethyl ketone or an aromatic solvent may be used in the solvent extraction process. Next, coming on to the base oil finishing process. So base oil finishing process, it involves to remove the polar components for the improvement. In the base oil, that is the lubricant oil, there are various polar compounds are present. That is aromatic compounds are present, which provides the color and smell to the lubricating oil, which needs to be removed. Okay. So to remove these polar compounds for the improvement of color and color stability and thermal stability of the base oil, early lubricant refiners used clay absorption process using fuller's earth or Attapulgos clay. These processes have been almost entirely replaced by hydrofinishing processes. So, in base oil hydrofinishing, the oil is contacted with hydrogen over a fixed bed of catalyst at low to moderate pressures, temperatures, and space velocity and gas rates. Impurities such as trace solvents from upper processes are removed, sulfur and nitrogen are reduced, and color stability is improved. So, hydrocracking of base oil reduces the aromatic contents by saturating double bonds or by ring opening and is becoming an increasingly important procedure for improving the lube oil base quality. Okay, so this is for today. This is the theory portion. Now, coming on to the assignment questions, the range of gasoline in the straight run cut from atmospheric distillation unit is considered roughly as. As I told in the early slides, the range of gasoline it varies up to C5 to 180 degree cut. Okay, so the answer is C5 to 180 degree C. The important gas produced during the reforming of naphtha is, as I told you in the various reforming reactions we have seen hydrogen gas is produced. Okay, coming on to the third question, which is semi-regenerative catalytic reforming process is the one in which the unit is periodically shut down to regenerate the catalyst. The unit is periodically shut down to regenerate the catalyst is correct. And the unit is periodically shut down to change the reactor. No, we do not change the reactor. We change the catalyst. We regenerate the catalyst. Okay, the naphtha feed is charged at two different reactors at two different times. No, this is not correct. And the catalyst of one reactor is used in the next cycle at certain period of interval. This is also not correct. Okay, so the answer is the unit is periodically shut down to regenerate the catalyst. Find out the wrong statement. The difference between semi-regenerative and continuous catalytic regeneration process of reforming. High hydrogen to hydro. Just a second. Okay. High hydrogen to hydrocarbon ratio is used in SR reforming compared to CCR. So this statement is correct because in the case of SR reforming, uh, mean continuous regeneration of the catalyst does not take place. So coke deposition, huge coke deposition takes place in the case of SR. So here the hydrogen to hydrocarbon ratio here it is taken almost 6:1, whereas in the case of CCR it may vary, it may go down up to 1.16 to 1 ratio, because in this case the catalytic coke deposition is not a problem. Higher coke deposition on the catalyst is tolerated in the SR process than in the CCR. This is also correct. Higher coke deposition takes place in the SR. So robust catalysts are used in the case of SR process, whereas in the CCR process, continuous regeneration of the catalyst takes place. So coke deposition is not a problem. Selectivity towards aromatics is more important in SR than in the CCR process. Okay. So this regeneration of the cycle time is higher. Regeneration cycle time is higher in SR than in the CCR. Yes, because in the case of SR, regeneration takes place single time. Mean after a long working of the SR reactor and complete exhaustion of the catalyst, regeneration takes place. So it takes a longer time in the case of SR, whereas in the case of CCR, where regular regeneration takes place, it does not take much time. Whereas the third statement, which tells the selectivity towards aromatics, is more in case of SR, which is wrong. The selectivity towards aromatics is more in the case of CCR. Okay. So the wrong statement is the selectivity toward aromatics is more important in SR, which is wrong. It is more in the case of CCR. Okay. Coming on to the fifth question, which is find out the incorrect answer. Catalyst for secondary processing of petroleum product required. Catalysts for secondary processing require good activity, good selectivity, and good stability, but it does not require good high metal content, which is definitely not required. It will deactivate the catalyst. So metal content is not required. This is the wrong answer. Coming on to the sixth question, which is alkylation process in the refinery involves the reaction between light olefins with isobutane, uses platinum or alumina catalyst, produces N-paraffin products, or is practiced in the FCC. So the answer is it involves the reaction between light olefins and isoparaffins. Okay, light olefins of that is C3, C4 fraction olefins. It reacts with all isobutane. Okay, choose the correct answer. Deasphalting is. It is an extraction process. Okay. Deasphalting is an extraction process in which the extraction of refined oil or refined lubricant oil from the as- from the asphalt takes from the mean heavy residue takes place, leaving behind the asphaltene content. Okay. Coming on to the difference between catalytic dewaxing process and the solvent dewaxing process is catalytic dewaxing removes the wax content in the feedstock by converting it into aromatics, whereas solvent dewaxing removes wax by solvent extraction. The first option is wrong because the second part is right. Solvent dewaxing it removes by solvent extraction, but solvent dewaxing is not converting the feedstock into aromatics. It is basically converting the N paraffins into isoparaffins or lighter fractions or lighter distillates. Okay. Coming on to the catalytic second option, which is so this is wrong. Catalytic dewaxing removes the wax cracking. Just a second. Okay, so the second option is catalytic dewaxing involves wax cracking and isomerization, whereas the solvent dewaxing is the removal of wax from the feedstock by solvent extraction. The second option is correct, similar to first one. And the first option, it involves catalytic dewaxing, it involves the wax cracking. Obviously, it involves wax cracking by converting it into smaller, lighter fractions of such as kerosene or naphtha and some amount of isomerization of these N paraffins into isoparaffins. Okay, so this option is correct. In the catalytic dewaxing, third option, which is in the catalytic dewaxing process, wax is precipitated out, whereas in the solvent extraction, wax forms the top layer, which is correct, which is not correct. Okay. And the catalytic dewaxing process uses methane gas in the process, whereas the solvent dewaxing uses methanol as the solvent. It is also wrong. Ninth question is the petroleum wax is it is long straight chain paraffin hydrocarbons or higher molecular weight isoparaffins or simple aromatic compounds or branch chain naphthenes. The answer is long straight chain paraffin compounds, as we know that waxes are long straight chain hydrocarbons. Hence, okay, so the answer A is correct. Coming on the last question, which is find out the wrong statement. The base oil finishing process involves the use of hydrogen. It is a catalytic process, reduces aromatic content or improves the octane number. In the last slide itself, we saw the base oil finishing process. It reduces the aromatic content since they contribute to the smell and color. Okay. So to improve the color stability and reduce the smells, need to reduce the aromatic content. Oh, just a second. Okay. Uh, According to me, this is the correct answer, but I'll let you know. I mean, in the slides, you'll get the correct answer. I'll give you the. Okay. So this is the correct answer. In the as we studied in the last portion, the base oil finishing process, it involves the reduction of aromatic contents to for color stability. Okay. So this is it for today. Thank you for your patience. Okay. So this is for today. Thank you everyone. And let me lead the class. Okay. Let's meet next week.